So welcome to our third lecture of Physics 157. And I'm usually going to start with a review of what we had last time. So we were talking last time about how thermodynamic properties of materials, they have to do with things that are happening at the molecular level. We talked about how energy is a quantity that is conserved. Any part of any physical system has a certain amount of energy associated with it, and it can take different forms, and it can be transferred between different parts of the system. The energy that we're interested in thermodynamics, well, one of the most important ones is the kinetic energy of the molecules in an object. And the difference between a hot object and a cooler object is largely a property of how fast are the molecules in that object moving or vibrating. So in a solid, the atoms or molecules are not moving around the material, but they are still moving back and forth, colliding with nearby molecules. And the speed at which these things are vibrating is going to be higher in a hot object compared with a cold object. We understood also last time that even though that's all going on at the microscopic level, and we can't really see those atoms or molecules, there are ways in which we can perceive the effects of this increase in kinetic energy of the molecules, because these molecular level effects actually change properties of the material at the macroscopic scale in ways that we can observe, even though sometimes it's subtle. So if I have either a solid or a gas or a liquid, one thing that I might notice is that as I heat it up, then it will expand. And this could be a very subtle effect for a solid, a brick. As I heat it up, it will actually expand a little bit, but you would need just a very accurate measuring equipment in order to detect that. Okay, but it's still detectable. In a gas, the pressure might increase. We'll talk about that later today. And then it would be more obvious. As you heat up a balloon, the balloon would expand. A liquid expands as you heat it up. This is the basis of a mercury thermometer. We also said that visibly objects can change. If they're very hot, then they might start glowing. But even for cooler objects, if you were to observe them using infrared light, as we did last time in the demo, you can actually see that as they heat up, they produce more infrared radiation, and the wavelengths of the infrared radiation that they produce will change. So just to consolidate some of the ideas from last time, I wanted to start with this clicker question. It's about two objects, each initially in equilibrium. They're put into thermal contact, and we assume that they're insulated from their environment. And we notice that object A, but we don't notice that heat flows from object A to object B. Maybe we're looking at these things with an infrared camera, or maybe we're carefully observing the sizes of the object. But we see that heat flows from object A to object B somehow. And what can we conclude? Can we conclude that object A had a higher temperature than object B? Can we conclude that object A had a higher energy than object B, or both, or neither? So pause the recording, think about that, and then we'll talk about the answer. Okay, so just remembering some things we talked about last time, one of the fundamental properties of the concept of temperature is that temperature is a quantity that will determine whether heat will flow from one object to another, or the other way around, or no net heat is transferred at all. Okay, I'll just remind you with this slide. So if you have two objects and you notice that no net heat is flowing between them, that's actually part of the definition of those objects being at the same temperature. So we would say they're in equilibrium, or they're at the same temperature. If you notice that heat is flowing from one object to another object, then we would say that this lower object is at a higher temperature, and this one is at a lower temperature. And same thing for the other way around. So in this case, if heat is observed to flow from object A to object B, we could definitely say that object A has a higher temperature than object B. What about energy? So if our two objects are identical, say we have two identical bricks and they're just beside each other and we see that heat is flowing from one to the other, well then this one has a higher temperature, but it also has a higher energy because the only difference is that its molecules are moving faster. They have more kinetic energy. But the question doesn't say that our two objects are identical. And so in fact, we can't really use the information in the question to conclude that one object has a higher energy than the other. Just to demonstrate that, imagine that you have the two identical bricks and one is hotter than the other. One has a higher temperature than the other. Okay. If they're identical, this one has more energy. But now imagine that instead of this hotter brick, we have a similar brick which is 1/4 of the size. So let's just say we cut it and throw away 3/4 of the brick. Well, now this second brick, it still has a higher temperature. The temperature didn't change. So this one has a higher temperature than the other part. But there's much less brick there. So the total amount of energy in this hotter second brick is actually going to be less. And so that shows that we can't really conclude anything about the total amount of energy based on which direction heat is flowing unless we make additional assumptions. So today we're going to get into how do we actually assign a number to temperature. So far we've understood that temperature is a quantity which is a property of an object, and it will determine whether heat will flow from that object into other objects or the other way around. So we could, in this picture, see that you have a brick and a balloon and a thermometer, and they can each be in equilibrium, say in this lower picture. They're all at the same temperature. If you place any two together, there won't be any heat transferred. And then this is, in the other bubbles, you have the same objects depicted at different temperatures. But now we want to understand, is there some useful way in which we can actually assign a number to the temperatures of these various objects? Okay, because when we think about temperature, we normally think about there being a particular specific number, even though there are different temperature scales. In any one of those scales, there's like a specific value for the temperature of freezing water or boiling water. So how do we do that? Well, the answer is just to use some property of one of these materials, and you can use that macroscopic property to define a temperature scale. Okay. So a common basis of a temperature scale is looking at the height of mercury in a thermometer. So I want you to think about this question a little while. This is basically having you think through exactly how you could define a temperature scale based on the height of mercury in a thermometer. Okay, so we're all kind of used to this idea, but it's good just to think through the steps that you would use. And so this question says, suppose that you're given a bunch of thermometers, but nobody put any markings on them. And so they're just literally mercury in a glass tube, and you want to now come up with a numerical temperature scale based on this tube of mercury. So you want to figure out what is the temperature in your room using this thermometer, but so far it doesn't have any markings on it. How do you do it? So pause the video, take a few minutes to think about that, and then we'll come back. Okay, so in the class, we had various suggestions, and I think a lot of the groups understood that, well, what you could do is try to calibrate the thermometer somehow by using some temperature, putting the thermometer, say, in water that has a particular known temperature. So one very easy way to make sure that water has a temperature that you know is to have water that's in equilibrium with ice. And you've probably learned that the temperature then is what we'd call 0 degrees Celsius. And so if you put the thermometer in the ice water and then you see where the level of the mercury is, you could place a marking on your thermometer that is 0 degrees Celsius. Then you could go and place your thermometer, for example, in some boiling water and wait until the thermometer comes into equilibrium with the boiling water, and then you could place a marking on that thermometer that says 100 degrees Celsius. And then at that point, you could just place equally spaced markings between 0 and 100. Now you take the thermometer out, you wait till it comes to equilibrium with your room temperature and with your room air, and look at where the level of the thermometer is, and then you could read off what the Celsius temperature is. Okay, so that would be a way to define what we would call the Celsius scale. What about this extra part? Will your method give exactly the right temperature? Why or why not? Are you assuming anything? So people in the class came up with a couple of really good points. Number one, well, are you sure that that ice water and that boiling water would be exactly at 0 degrees or 100 degrees? Okay, so sometimes if you're, say, at very high altitude, then you may know that water boils at a slightly lower temperature than 100. And similarly, the freezing point of water also depends on the pressure. So if you want to be really accurate, what you need to do is control the pressure as well as the temperature, and then make sure that you're at a pressure where the boiling point of water is exactly 100 and the freezing point of water is exactly 0. Okay, we'll talk about a specific, precise way that a different temperature scale, the Kelvin scale, is calibrated, probably next lecture. Another assumption that we've made in defining this temperature scale is that by placing equally spaced markings between 0 and 100, we were assuming that the liquid in the thermometer is expanding linearly with temperature. And so if that happened not to be true, so in reality, using the actual Celsius scale, which is defined in a slightly different way, the volume of mercury, as you increase the temperature, it actually is slightly curved if you were to plot the volume versus the temperature. And so there's some slight inaccuracy if you put the spacings equally marked. Sorry, if you put the marks equally spaced, there's some slight inaccuracy. And actually, I'm going to have you think about that quickly in the next quick clicker question here. So this is supposed to be a graph of the actual volume of mercury versus the true temperature scale, the true Celsius temperature scale. And so I want you to think about if you had simply placed equally spaced marks on the thermometer, then you put the thermometer in the water, or whatever it is. If it reads exactly 50 Celsius on your thermometer with equally spaced markings, could you say that the actual temperature is exactly 50, or is it a bit higher than 50, or is it a bit lower than 50? So maybe pause the video, think about that, and then come back. Okay, so I want to demonstrate the answer to this question by just drawing a picture here. Okay, so hopefully we can see this. Should give me a moment here. I'm going to get this up on another screen so I can make sure it's showing correctly. Okay, so while we're doing that, I'm going to draw the graph that we had. So we have the volume versus the temperature. I've exaggerated that a little bit. So let's say this is 0 and this is 100. I'm just pulling this up here to make sure that we can see this properly. So on my main computer screen, I just see the slides, so I can't watch the video at the same time, but I've got my separate computer going here. Okay. Just taking a minute. Okay, anyways, while I'm doing that, I will just draw a line. So here's 100, here's 0, and basically by placing the marks equally, we've kind of assumed that the expansion of the mercury is linearly increasing with temperature. Okay. And then what we did was to say, okay, this is 100. This is exactly half the volume at 50 here. And we said, okay, that we concluded that if you are at a mark which is half of the maximum volume, that the temperature would be 50. Okay. But this isn't the real graph of how mercury expands. This was the real graph. And so we notice that if you look at the place where you're halfway between the volume at 0 and the volume at 100, and then you look at the real graph, you see that the temperature is actually a little bit higher than 50. So this is probably greatly exaggerated, and so maybe it's 50 point something, 50.1 degrees, something like that. Okay, so there you can see that. So I'm gonna go back here. All right, so you can see me again. And so the answer to that question is that the actual temperature is a little bit higher than 50 degrees. Okay, that's kind of a bonus, a little bit subtle. Don't worry too much if you didn't get that the first time. Okay, so we've talked about now defining a temperature scale based on the volume of mercury in a thermometer. You could have chosen other materials. There's many possible materials that we could have based our temperature scale on, and there's actually many possible properties. So you could think about gold and measure the intensity of infrared radiation coming off the gold. So there's all sorts of things you could imagine as ways of assigning a number to temperature. Is there one simplest way or some preferred way? Well, there is actually a particular way of defining temperatures that maybe scientists have settled on as being the simplest. And that simplest way, the sort of nicest way of defining a temperature scale, it basically starts by using the simplest possible material. And the simplest possible material is one where the molecules just don't interact with each other at all. So it's not a solid or a liquid, it's a gas, and specifically, it's this idealization of a gas that we call an ideal gas. So an ideal gas you can think of as just a bunch of molecules that are independently moving around inside a container, and maybe they can collide with the walls, but we assume that they don't have any significant attractive forces between them or repulsive forces between them, that we can more or less ignore the interactions between the molecules. And so this is an idealization, but it's a pretty good approximation when you have a very low density gas. So our temperature scale is going to be based on a property of an ideal gas, which is the pressure. And so the way that we're going to imagine defining a temperature scale is to put an ideal gas inside a container with some particular fixed volume, put a pressure gauge on there, measure the pressure, and then we'll say that the temperature is directly proportional to that pressure we measure. So I want to just remind you quickly, since it may be a while since you saw the definition of pressure, I want to remind you, what does that really mean? What does pressure tell us about a gas? So I have just a quick slide and then a clicker question to have you process this. Okay, so pressure has to do with the force with which a gas presses on the walls of its container. And so specifically, if we think of the gas in this container here, and we think about a certain area of the wall of the container, then there'll be a certain force on that area. And the force will be greater the larger the area that we look at. In order to define pressure, what we do is we divide the force by the area. Okay, so the pressure is the force per unit area that the gas is pressing with on the sides of the container. The unit for that is, we can see from the formula, it would be newtons divided by meters squared, and that's the SI unit called a Pascal. So 1 Pascal is 1 Newton per meter squared. So if you remember, ordinary pressures are quite large in terms of pascals. Air pressure in the room would be about 100,000 pascals. We usually say 100 kilopascals. So I actually want to do a quick calculation. I want you to think about how much force is this air at 100 kilopascals exerting on, say, the top of your head. So this is the clicker question here. The air pressure in the room is about 100 kilopascals. Assuming the top of your head can be approximated by a 10 centimeter by 10 centimeter rectangle, how much force from the air is pressing on that rectangle? Okay, and we want to say, to understand it, what amount of mass sitting on the top of your head would be an equivalent force? So I will let you think about that, pause the video, work it out, and then I'm going to go through it. Okay, so let's work this out. The idea is we have a 10 centimeter by 10 centimeter rectangle. And I'm going to go ahead and put that in SI units. So 0.1 meters by 0.1 meters. And we have some force from the air pressing down on this rectangle. It's actually a square. Square is a rectangle. So how much is the force? So using our definition of pressure, so we had P equals F over A. And so if we rearrange that, that tells us that the force is going to be the pressure times the area. And the pressure was 100,000 pascals. And then the area is 0.1 meters squared. And so altogether, you end up with 1,000 pascals times meters squared, which is newtons. So 1,000 newtons is the force that's pressing down on your head from the air in the room. How much is that in terms of if we wanted to compare it with a weight that might be sitting on your head? And so there we should remember that the force from a mass due to gravity is m times g, where g is it's 9.8 or approximately 10 meters per second squared. And so if we want to calculate the mass in this case, the mass is going to be the force divided by the acceleration of gravity. And so that's 1,000 newtons divided by 10 meters per second squared. And so that's going to be approximately equal to 100 kilograms. Just bring us back here. So I think that's fairly surprising. To me, that is kind of mind-blowing that the air in the room is actually pressing down on your head right now with a force that's equivalent to a 100 kilogram mass. why don't we feel that? Is that right, or did I make a mistake? So the answer is it actually is correct. It's pressing down with that much force, but we're just totally used to it. So the way that we can understand this is that that same force is pressing on all sides of our body, and just the material that we're made of is not really compressible very much, the liquid in our body. And so somehow, even though there's this enormous force pressing everywhere on our body, we're just used to it. It doesn't crush us. We're just kind of used to that. And if you were to take away that force, then you would notice, and you wouldn't be very happy about it. So if you think about it, if you take away that force in just a little part of your body, so let's say this part of my skin, if I removed the air there, well, that's what a vacuum does. So if I had a super powerful vacuum cleaner that was able to suck all the air away from my arm there, what would you feel? Well, you would feel you would feel this painful suction, and all the blood would go to your skin, the surface. You would get a big bruise there, and so it would actually be very unhealthy if we took away the air. If you're out in outer space and you didn't have a space suit on, you would not last very long. But maybe you don't believe me, so I want to actually do a demo to show in practice this force of air actually doing something. So what I have here is I have a glass of water. Let's just take the camera here. I have a very full glass of water, and what I'm going to do is place. This is a piece of plastic. I could have used a card or really anything else that's flat. You can try this at home. I'm going to place this on top of the glass of water. Okay. Actually, I'll fill it up here so it's completely full. So I'll just add a little bit more there. Now it's completely full. And so now I will place my card on top of the water. Okay. And so now what I'm going to do, let me just put this here. Take this up. Okay. So all I did is I took this piece of plastic, I placed it on top. Okay. It's still moving around. It's not attached in any way. And what I'm going to do is invert that now. Okay. And so right now what's happening is that there's water in the glass and it's pressing down on this plastic. And it's quite a big glass, so it's quite a lot of water. I would say something like 750 grams of water. And the only thing that would be holding this plastic up is the air below it. So I'm going to take my hand away and see if the force of the air, so if I'm right in the last slide, if our calculation was right, there's a lot of force from that air pushing up on this piece of plastic. And it should be enough to hold up that 750 grams of water. So here we go. I take the hand away, and it's kind of amazing. Now we're looking right up on the glass from below, and the water is just sitting there being held up by the air below the glass. Okay. So here we go. Turn that back up. Dry the floor, or a few drips. Okay. So there it was. You could try this at home. Get a cup of water, get something flat, fill up the cup right to the top, place it on top, and invert. I would recommend doing it in the kitchen or the bathroom over a sink or a bathtub, just in case. Probably don't do it in the vicinity of all of your computer equipment like I just did, unless you really feel confident. It's amazing. Every time I do it, it's amazing, and I just can't believe when I take my hand away that the air is able to hold the water up. So how do we understand this? How is it possible that this air, which we hardly even notice, is producing enough force to keep that water from pressing the plastic down and falling all over the floor? So I'm going to show you a simulation just to help visualize this. Okay. There we go. So what we've got here is a simulation of a gas, of an ideal gas. And so these red objects are molecules or atoms, and they're just bouncing around. So if we think about the molecules in the air, there are really a lot of them, number one, and they're actually moving very, very fast. And so there are many, many, many collisions happening all at once, even though each collision is a little bit of impact. All together, all of those air molecules hitting that bottom of the plastic ends up adding up to a lot of force. So somehow, even though we don't see it, there's really a lot going on at this molecular level again, and it can have very significant macroscopic effects. It's totally invisible to us, but there's an enormous number of collisions that add up to a force that's enough to hold up actually quite a bit of water. In fact, if you calculate it, if you think about how much water, how tall of a column of water could you hold up using air pressure, it's actually quite large. So that would be a good thing to give it a try if you want to think about that. How much water would the force of air be able to hold up, be able to balance against? Okay. All right, so our point there, the reason we introduced the ideal gas was that I claimed this would be a good material to base a temperature scale on because it's a very simple material. And we're going to base our temperature scale on the pressure of an ideal gas in, say, a constant volume box like this. So to understand that, I just want to show you what happens if I were to actually heat up this box filled with gas. So that's what's happening in the simulation. So I'm heating up the box filled with gas. I'm increasing the temperature. And you notice what happens is that these molecules are moving faster and faster and faster. So as I increase the temperature, whatever external thing is causing this to heat up, that has molecules that are colliding with the walls of the container, and then the walls of the container are moving fast. They collide with the atoms or molecules in the gas, and now they're moving fast. And so if you notice now, the pressure actually, originally it was at 8 or 9 atmospheres. 1 atmosphere is the pressure of our room, and now it's up at 37 atmospheres. Okay. And so this is the way that we can define a temperature scale. We just attach a pressure gauge to measure the force of the air, and then we define a temperature based on that. Okay, so I'll go back to my slide here. So literally, we just read off the pressure from the temperatures from the pressure gauge, and then define the temperature to be proportional to that. So the only thing we have to do, so we set up this thermometer like this, we set up the pressure gauge, and then the only thing we have to do is choose some proportionality constant. In other words, we need to choose where do we put the markings on our pressure gauge for various temperatures. And we'll talk about specifically how to do that the next time. But this is the definition of the Kelvin scale. All right, so that's it for today. And we're going to come back and complete our definition of the Kelvin scale next time.